technical educational film on lining and induction furnace, produced by RK Technical Training and Research Institute, sponsored by Calderys India Private Limited and Inductotherm India Private Limited. Presented in conversation with Mr. Shyam Kulkarni and Mr. R.R. Rao.
The refractory lining of an induction furnace plays an important role in its operation and performance.
Correct installation and maintenance of lining will enhance the lining life and will definitely reduce the cost of liquid metal production.
A correctly lined and well-maintained refractory lining is absolutely vital for the safe operation of an induction furnace because it plays the critical role of protecting the induction coils and preventing metal runout in case of emergencies such as attack by molten metal, chemical agents and mechanical shocks. In this figure, we see a schematic diagram of an induction furnace. These are the coils through which the current passes. These coils are grouted with a thin layer of refractory cement. This shows molten metal. This is the refractory lining which holds the molten metal and protects the coils from damage by molten metal. It could be basic, namely magnesite, or it could be acidic, namely silica, or it could be neutral, namely alumina. Poor lining practice and bad maintenance can not only result in loss of production and high cost, but may cause serious accidents. In the next few minutes, you will see how to inspect and test lining material, how to judge when to tear down the lining, and how to remove the old lining and get ready for relining. Causes of lining wear. Refractory wear is caused by slag attack, attack from the melt, thermal stressing, mechanical stressing, erosion. Patterns of lining wear. A number of different patterns of lining wear can develop as a result of some operating practices. The most desirable type of wear, giving maximum lining life, allows instrument readings to give a good indication of lining conditions. More often found in holding furnaces in which the metal level fluctuates between a high and low level. Greater contact time between melt and lining wear in lower areas of the crucible causes greater erosion. Caused by either holding small heel of metal at high temperatures for extended times or by bridging of charge materials whilst on high power input. Result of poor charging practice. Erosion by scrap during charging of furnace. Rapid slag attack at metal surface caused by low melting temperature, favoring increased rate of metal oxidation. Use of highly oxidized charge materials. Excessive metal turbulence at surface. Caused by slag attack in holding furnace with fluctuating metal level. Desulfurizing slags from porous plugged ladles or shaking ladles also cause this pattern of wear. Occurs in some older designs of furnace due to inadequate cooling below the power coil rather than bad practice. Measurement of lining wear. It is very important that the furnace operator should be aware of the changing condition of the crucible at all times. This can be achieved by measuring crucible diameter at various locations when the furnace is empty. Inspecting the lining visually for local erosion or cracking. In holding furnaces where a molten heel is always retained, this inspection should be carried out whenever the furnace contents are at a minimum. Repair of linings. Small hairline cracks which can appear on cooling will normally close when the furnace is heated. Larger cracks, grooves or small spalled areas can be effectively patched with a plastic siliceous refractory. Erosion of the crucible bottom can be repaired by pouring lining material into the furnace bottom, ramming with a flat rammer, and if it is a large area, covering with a steel plate. A small starting block should be used to hold the plate and lining in place during the first melt. This should be avoided in medium frequency furnaces as GLD antenna will get disconnected by bottom patching. Erosion of the lower side walls and the bottom can be repaired using a half former having a diameter slightly less than the original diameter of the lining. The lining should be well cleaned and the bottom lining material rammed in place. The half former should be positioned and the space between it and the wall rammed with lining material. The top of the patch is sealed with a plastic siliceous refractory. The subsequent heat up should take about as long as the fitting heat. Slag line erosion is rather more difficult to repair, and many people prefer to knock the lining out and install a new one. However, in the middle of the week, production would be lost and some form of running repair may be attempted. In cold melting operation, the erosion may be patched with a plastic siliceous refractory between heats. There are 4 stages in installing a lining. 1. Inspection and testing. 2. The ramming and the refractory material. The furnace. The tools and former. 3. Pre-warming. 4. Sintering the refractory. Let us see these one by one. First, inspection and testing the furnace. The condition of the furnace can seriously affect the performance of a newly installed lining. Hence, it is important to check the furnace before lining it. Tighten all nuts, bolts and joints to minimize vibration. When power is turned on, the alternating current passes through the coils and causes vibrations in the mechanical parts of the furnace.
Mr. Kulkarni, why is it necessary to tighten the nuts and bolts in the furnace before starting relining?
During melting operation, because of vibration, the nuts get loose. Then again, because of heating and cooling of the tie rods, this gets loosened. So it is necessary to tighten before we do the lining. Or I will insist that this should be done periodically also in between at your weekly maintenance day. If this is not done, what happens because of the expansion of the refractory, the top blocks gets lifted and there is a damage to the top block. To avoid this, it is necessary to do the tightening of nut bolts and tie rod periodically.
Vibration causes segregation of the particles, resulting in pockets in the partially sintered lining. If the coils have been changed, make sure that they are concentric with the furnace structure. Coil grout should be applied with minimum water for troweling and not more than 3 to 5 mm thick in smaller furnaces and 5 to 10 mm thick in bigger furnaces. For furnaces where the hydraulic push-out method for lining removal is adopted, adequate taper should be given to help in removal of the lining.
What are the properties of a good coil grouting cement?
Coil grouting cement, as name says grouting, this means we are increasing the mechanical strength of the coil, because coil, you know, it is in the form of spring, and by applying a cement on the coil you are making it in the form of cylinder. So that first purpose is to increase the mechanical strength of the coil. And when we apply this cement, it should be very smooth on the coil. It should be like a plaster of our wall, because if it is very smooth, then it will permit the vertical expansion of the refractory and will not give any damage to the coil. Second thing, this coil grouting cement has to have the electrical insulating properties, so that there is no interturn sparking between the coil. And another property, as I told you, it should have good strength. So these are the only two properties required, because the refractoriness is not important at this case, because it is not coming in contact with metal. It is always in contact with the coil, which is water cooled. So the strength and the electrical insulating properties, these are the two properties important for coil grouting cement. After application, you need to dry it in air for 24 hours, then another 24 hours with the heater, so that the total moisture is evaporated. I will not advise you to have any shortcut on drying operation of the coil cement. This is very important when the total cementing of the coil is done for the first time, or if you remove the coil and do it a new coil coating, this is very important. So care is to be taken when the coil is new or the total cementing is to be done.
Coil grout is available in three varieties: silica base, magnesite base, and alumina base. The size should be less than 1 mm to give good finish, and it should not contain magnetic particles, and it should develop good strength and should have electrical insulating properties. Any uneven projections in the coil coating will interfere with the free upward expansion and contraction of the sintered lining during use, and may cause cracks in the lining. Use demineralized water for circulation in the coils to avoid deposition of scale in the coils. If the furnace is of old design, this may not be available. In that case, regular descaling should be carried out with a descaling compound. Inspection and testing of refractory lining material. There are three types of lining material. They are acidic, silica with boric acid or boron oxide; basic, magnesite; neutral, high alumina. Silica linings are normally used for all grades of cast iron. Ensure sufficient stocks of proven quality and pre-tested lining material, and use on first in and first out basis. Store the material properly and have a separate store which is clean and dry for storing the ramming mass. Place logs on the floor before stacking the bags to prevent moisture absorption through the floor. Cover with tarpaulin to keep out harmful dust, and do not store coke dust, bentonite, fire clay, etc. near the ramming mass. Silica ramming mass is available with and without premix binder. The binders commonly used for silica are boric acid and boron oxide. The percentage addition depends on operating temperature, as shown in this graph. This is Swedish quartzite with premixed boron oxide ramming mass. This is alumina magnesia spinel forming dry vibratory ramming mass. Ramming mass with premix binders give better uniformity and assured consistency and save mixing time on the shop floor. It is better, safer and easier to use premixed ramming mass than to try and mix the binder on the shop floor. Addition of too much binder by mistake may drastically reduce the refractoriness of the ramming mass and result in high lining wear and probable puncture of the lining and coil. Keep the two, mixed and unmixed ramming masses, separate and clearly labeled. If you suspect any mix-up, the lining material should be scrapped. If, however, you prefer to mix your own ramming mass, stick to this only. Keep only one type of ramming mass to avoid mix-up. All types of ramming mass should be tested before use for moisture, bulk density, iron particles, and sieve analysis. Do not use ramming mass bags showing water stains or moisture content above 2%. Test the ramming mass for loose bulk density. Silica 1.7 grams per cc. This may vary as per the source. Basic material 2.0 to 2.7 grams per cc. Packed bulk density of silica should be 2.0 grams per cc. Packed bulk density of magnesite material should be 2.5 to 3.2 grams per cc. Check for sieve analysis on 0.6 mm 30 mesh and 0.1 mm 150 mesh sieves.
How important is the sieve analysis of the ramming mass?
First thing is sieve analysis is done to decide the AFS number of any material. Normally in sand we will perform this test for sand to find out its AFS number, because in sand what we use in foundry, the 3 sieve distribution is very important and the AFS number is important. But in our case the ramming mass has to have a good compact density and permeability is not of importance in our case. The compact density is more important. So even if we do the AFS analysis and find out the number, it should not be the criteria for accepting or the rejecting the material. The compact density is more important and the distribution of this grain size is decided by the manufacturer to achieve the best compact density. So my advice is that AFS number is not so important in our case. If you want to carry out the test for AFS analysis, fine, but don't go by the number and accept or reject the material as per the AFS number what we get in sieve analysis.
Mixing of boric acid with silica.
Can you comment on the use of boron oxide?
Boron oxide is a replacement of boric acid, because as you know, boric acid contains nearly 50% of water, and during sintering you have to remove this moisture and this takes a long time. This can be avoided by using boron oxide because it has no moisture, it is anhydrous boron oxide. The addition is less, so mixing precaution is to be done. It has to be mixed very properly with the help of some concrete mixer or machines. And by using boron oxide, as I said, there is no moisture. We can reduce the sintering cycle time. We can do the liquid sintering when boron oxide is used. Only one disadvantage is that it is an imported material, so it is a costly. So some people are using boron oxide, some people are very comfortable with boric acid.
Use separate trays for heating and drying and for mixing. Heat the drying tray with gas if possible and available. When using oil burners or charcoal and firewood, Beware of spillages that can contaminate the ramming mass, bags or containers. Aim for drying temperatures of 70 degrees centigrade if binder is premixed. Otherwise, 100 degrees centigrade or so. Stir the ramming mass frequently while heating. If it is noticeably damp and the powder sticks to the palm after holding a fistful, then it will require a couple of hours of drying out. If drying is insufficient, the steam formed on sintering will open up crack, forming passages in the lining. Then transfer it to a cooling tray before mixing, in that same tray or in a mixer. Cool the ramming mass until it is so cool that you can hold it in your palm to the count of 10. Demagnetize and heat a second batch while the first is cooling. Boric acid loses its first molecule of water at 80 degrees centigrade. If boric acid is added while the ramming mass is too hot, it will melt to form globules and cannot be distributed uniformly. This may allow pinhole-like defects to be seen in the lining surface. Make a premix with the boric acid by doubling and redoubling. In a basin, mix thoroughly by hand the required amount of boric acid with an equal quantity, say 1 kg of dried ramming mass. To this mix, add an equal quantity, say 1 kg of ramming mass and mix again by hand. Repeat once or twice more. This uniformly diluted lot may then be mixed with the remainder of the batch, preferably by doubling and redoubling as above, or by sprinkling the premix on the rest of the batch and turning and raking. Do not sprinkle undiluted boric acid for mixing. Its volume is too small for uniformity. Even if a mechanical mixer is used, add the boric acid in a diluted premix as shown for more uniform distribution. Check your mixing practice for uniformity once in 2 months, or when a new workman is doing the mixing, or for the first 5 linings in the case of new users as follows. Add ultramarine blue in powder form, 50 grams per bag of 50 kgs to each batch. In the same way as you add boric acid premix and mix the batch as described. Mixing is uniform when the whole batch has attained a uniform color. It is quite harmless to the lining. For mechanical mixing, check the performance of the equipment periodically. Add ultramarine blue in exactly the same way that boric acid premix is added and along with it. After emptying the mixer, look for blind corners or pockets where the color may not have reached and take corrective action. Place a tall screen around the working furnace so that sparks flying from an adjoining furnace will not contaminate the ramming mass being preheated, nor will it fall into the furnace being relined. Getting ready for lining. The former. The mild steel former used for forming the inside shape of the rammed lining should be clean, that is, free from rust, paint, etc. It should be rigid, that is, it should retain its shape during handling. It should be truly circular, and it should have 3 mm diameter perforations at intervals of 100 mm to allow escape of steam during the initial heating. It should preferably be short blasted just before use. You are now ready to begin installing the lining, which protects the induction coil from the heat of the molten metal.